Hi, today we are looking at graphing sine and cosine functions in our trig graphs. So we're going to take a couple of minutes and review a few things before we get started, and then we are going to be unwrapping the unit circle and coming up with our sine curve. And so today we're specifically looking at sine and cosine. These are important graphs to get because as we venture into our next assignment, which is graphing secant and cosecant, you have to use the graphs of sine and cosine to get you there. So that's kind of important to make sure we know how to do this. All right, so first couple of things, I want to talk about some new terms. The first one is what we call the period of the function or the cycle of the function. That's the length of one cycle of the trig graph before it starts to repeat, in other words, one period. Most graphs will require you to graph 2 periods of a function when you're graphing. Unlike your functions from Algebra 2, where you just kind of graph the absolute value or graph the quadratic and it was done, trig functions are what we call periodic functions. So they periodically repeat the pattern. And so every period is one graph. So usually we will ask you to graph 2 periods of the function. The amplitude is another new term. The amplitude is half the distance between the maximum and minimum values of the trig function. And so we actually say the absolute value of a because we don't really care if it's a positive or negative direction. The only functions that have an amplitude are sine and cosine. So those are the ones that you possibly would be finding the amplitude for. And that's because the sine and cosine are the only two trig graphs that have an actual high point and a low point for you to be able to determine that from. The other thing to keep in mind is if a graph is translated up or down, then the trig function, obviously the middle of the trig function will be on the x-axis, the horizontal axis. But if the graph translates up or down, the graph goes with it, so that middle line does move. If your middle line moves off your horizontal axis, you will need to draw a new middle line with a dotted line to represent that middle place on the graph. One of the things that we want to be sure we do is to calculate the period and amplitude before we begin the graph, at least the amplitude for the graphs that have them, which both of the ones we're looking at today do. Okay, so a real quick review of transformations. The difference is the way it's written. So you can see the general trig form for all 6 functions is y equals a, which is your vertical stretch or compression or reflection over the x-axis. Whatever the trig function is, sine, cosine, tangent, cosecant, secant. Then you have your b isolated, so your horizontal stretch or compression. You have your c, which is your horizontal shift left and right. You're translating that left and right. And your d back here, which is the movement up or down. So all of these are things that we've talked about in Algebra 2. You can find this help sheet in the trig help sheet section on Canvas. The last thing I want to remind you of is the transformation points. Remember, we spent a lot of time in Algebra 2 learning how to use transformation tables. Well, those are still hanging in there. It's different in pre-cal because sometimes you may need the transformation table to help you figure out something correctly, and other times you might not. For instance, if you were just transforming a graph up 2 points, you could just take the parent function and move it up 2 points. You spent a lot of time in Algebra 2 learning how to do the transformation table, so you have that skill in your pocket if you need it for one that gets to be more challenging. Or oftentimes folks will use the transformation rules and tables, especially when there's a horizontal stretch or compression, because that means your graph and your markings on your graph are going to change, and a lot of times it's easier to figure out what those markings are if you're looking at the transformation table. So again, you can find this sheet in the help section. So what we're doing now is I'm going to go over to my calculator for a minute, and we're going to show you the blue right here is the unit circle, and the red is where we've unwound the unit circle from that rotation. So let me let you see. It's going to graph these simultaneously so you can see the point coming off the circle and where it would be on the graph. Yeah, so this little red wave here becomes the first quadrant, the second quadrant, the third quadrant, and the fourth quadrant of that circular graph. So we're working with stuff you already know. We're just kind of translating it out now into a horizontal graph. So basically, This is your circle, your unit circle. So here in green is my first quadrant. So when that unrolls onto a coordinate graph, there's the first quadrant. The blue right here is the second quadrant. So when it continues the cycle around the circle, it comes to there. The pink is the third quadrant. So you can see the pink quadrant is right here. And the fourth quadrant would be that last little piece. And once the graph gets right back there, it has completed one circle, or one revolution around the circle, and we have this nice sinusoidal curve, which is an S graph. So unit circle graph using the quadrantal angles. So the parent function points for this sine graph would be the angle, which in this case would be 0, and the sine value of that angle. So if I'm at 0, I'm right here, and the sine value is the second coordinate, which is 0. If I'm up here where my angle is pi over 2, the sine value is 1. If I'm over here where my angle is pi, then my sine value is 0. And if I'm down here where my angle is 3 pi over 2, then my sine value is negative 1. And then all the way back around to 0. So that's my parent function points for sine. So it's just as easy to get the ones for cosine, because instead of using the sine values when you work your way around the unit circle, you would be using the first coordinate, which would be the cosine values, all the way around. So that's the process, or what we're getting ready to do. So let's talk about getting the sine graph, the first one. So first off, here's my quadrantal angles. Remember that the coordinate is cosine theta, sine theta, and the quadrant, and we're going to look at the quadrants around to determine what point we're using on the graph. So if we're doing the sine graph, we'll be using the ones in yellow, and if we're using the cosine graph, we would be using the numbers in orange. All right, so first thing, let's talk about the sine wave. So if we continue this pattern back here, imagine it's going to go down, and it's going to come up, and it's going to go down. And so if you look at that actual graph and you spin it 180 degrees, like we talked about in Algebra 2, then you would see what you started with, which means that the sine function is an odd function. So remember the transformation rule I showed you at the very beginning where it said trig? Well, in this case, the trig is the sine. So this is the sine function. So vertical stretch or compression, reflection over the x-axis, horizontal stretch or compression with a scale factor, horizontal shift left or right, and vertical shift up and down. So if it's an odd type function, then we know the sine of negative x is equal to negative sine of x. And all of these 4 points on my quadrantal angles are now stretching out to make a nice pretty sine wave. So that's what y equals sine of x looks like. We have the parent function. We talked about period is how long it takes for one cycle to occur. So one period of sine starts here and ends here. So how much is the period? Well, it's right here, 2 pi. Okay, if you are doing the amplitude, then the amplitude, remember, is half the distance, so it's up 1 and down 1. So the amplitude are those two extreme values. And our parent function points. Okay, so cosine, same thing, just using different points. But you can see that the cosine graph looks a little bit different from the sine graph. The unit value points, so if I'm up here at 0, then I'm at 1, and if I'm at pi over 2, I'm at 0, and if I'm at pi, I'm at negative 1, and if I'm at 3 pi over 2, I'm down here at 0. So those are the points that get brought out through my curve, and you can see that the cosine graph is a V graph, where the sine graph is an S-shaped graph. So if you imagine this graph continuing, you can see it would be like a little W, and I can fold that W in half on the y-axis, which means it's symmetric with respect to the y-axis, so it is an even classified function, which means cosine of negative x equals positive cosine of x. So these are our rules we learned from Algebra 2 as well. The amplitude is, again, absolute value of a, so we're looking at that half that distance to go up and half the distance to go down. The period is the time it takes to complete the graph. So in this case, the graph starts here, ends here, takes it all the way to 2 pi, which means it's got a period of 2 pi just like sine does. But it does look different. If you have a b value, then that does change the period, because remember, that's horizontally stretching or compressing. So that's making the graph happen more rapidly, or it's stretching it out and it's taken longer to complete the cycle. If that is the case, Then we take our 2 pi, which is the normal period, and we divide it by whatever the b value is. Not its scale factor, but the b value itself. So for instance, if I had y equals sine of 2 theta, b is 2, so I take 2 pi divided by 2, and now I know that my new graph would have a period of pi, which means, if you look at this graph right here, that means that whole v would have to happen by the time it got to pi, which means by the time we got to 2 pi, 2 of those v's would happen. And that's where you start getting that connection between the 2 and there's your b value. Okay? And then our transformation point, which we already talked about on the review. All right, let's start with 1a. We're going to go through these graphs real quickly. I know that you can read through them, so I just want to touch base on a few things as we go through it. Anytime you do these graphs, I would like for you to determine the period and amplitude first, and then you can use your transformation points, your transformation table, whatever you need to get the graph. So for instance, x over 2 is the same thing as 1/2 x, which means your b value is 1/2. So you're going to take 2 pi and divide it by 1/2, which is really multiplying by 2. So the period is 4 pi. It's now going to take all the way out to 4 pi for one period or one S wave to occur. The amplitude is 1, which means from the middle line you go up 1 and then down 1. So what are the transformations that are happening here? When that 1/2 is inside, you get a horizontal stretch or compression. In this case, it's a stretch. So the scale factor is 2, so it's stretching all the way out to 2 to be able to complete one cycle. So transformation point wise, if you think in terms of algebra 2, you think 2 theta sine theta. So I look at my parent function points, and I'm going to multiply all of the angles by 2 and keep all of the sine values. So 2 times 0 is 0, 2 times pi over 2 is pi, 2 times pi is 2 pi, 2 times 3 pi over 2 is 3 pi, and 2 times 2 pi is 4 pi. And then all of these values stay the same because there was no transformation that affected them. So the two graph options that I have here, a lot of this will depend on your teacher. Some teachers prefer that you keep the standard 0, 2 pi, pi, 2 pi graphing, and then you fit your points in between. Some teachers are okay if you adjust the axis, as long as you're not like extending out here into space somewhere. So you do need to check with your teacher to see what she prefers, if you're from one of the other sections. So as far as my graph goes, I changed the first one, all of them to be our new angles. So I have angles of 0, pi, 2 pi, 3 pi, 4 pi. And then I plotted my sine values. So at pi I was at 1, I was at 0 at 2 pi, I was down here at -1 for 3 pi, and back up at 0 for 4 pi. So you can see the wave doesn't look any different because I actually just changed the axis, the points on the axis. So it should look the same. However, in the second one, I went ahead and went out to 4 pi, keeping the traditional pi, pi over 2, pi 3 pi over 2, and 2 pi, and then fit the other points in between. So you can see here's 0, here's pi over 2, here's pi, here's 3 pi over 2, here's 2 pi. And so that would be 1/2 of this wave. And so I'd have to do that again to get the second half, which means that one period isn't ending until I get all the way out to 4 pi. So this one we would put in the points that we needed to help stretch it out. So there you can definitely see the transformation. All right, so 1b, you have y equals 2 cosine of 2x. The amplitude, remember, is the number in front of here. A is always that vertical stretch or compression, so you're looking right there. You take the absolute value of it, and that's 2. Well, what that means is you have a vertical stretch, so you're going from the middle line up to and from the middle line down to. And so then 2x means that you are having a horizontal stretch or compression, and so you would take 2 and the scale factor is 1/2, and then if you're finding the period, you use the b value itself. So 2 pi over 2 gives me a period of pi, which means from here to here is 1 period, and from here to here when I get out to 2 pi is 2 periods. So can you see how it's compressing down, and now there's 2 v graphs in the same distance it would normally take us to get all the way out here to have one V graph, and that's where that horizontal compression is happening. So then in terms of what I do to my graph, the 2 is going to be multiplied by the function value, and the 2 inside is a reciprocal 1/2, which is going to get multiplied by the x value. So our transformations here take us to the transformation point of 1/2 theta 2y. And so I take my angles and I multiply them by 1/2, and then I take my y's or my cosine theta values and multiply those by 2. So I get 0. I get pi over 2 times 1/2 is pi over 4. Pi times 1/2 is pi over 2. 3 pi over 2 times 1/2 is 3 pi over 4. 2 pi times 1/2 is pi. And then I multiplied all these cosine values by 2 and got 2, 0, negative 2, 0, 2. So then you can kind of see where I adjusted these marks so you could kind of see how that fit together. And I have graphed 2 periods of pi. So as you go into 1c, you have the y equals negative cosine of 4x. So again, we always want to start with amplitude and period. The amplitude and period for this one. So right in front of cosine is 1, so that would be absolute value of negative 1, which is 1. And then the period right here, the b value is 4, so 2 pi divided by 4 gives you pi over 2. Okay, the pi over 2 is your period now, so just think about that in terms of from 0 to up straight above where pi over 2 is. That's one whole repetition, one whole period is going to happen there. And this negative in front has turned it upside down. So we know we have a reflection over the x-axis and a horizontal compression by a scale factor of 1/4, which makes my transformation point 1/4 theta minus the y value. So negative 1 times the y value. So now we're looking at our cosine parent function points, and we're going to multiply each of the angles by 1/4 and each of the cosine or y values by negative 1. So when you do that, you get this new table right here. And when I plot those points, I can see I've got 0, negative 1, pi over 8, 0, pi over 4, 1, 3 pi over 8, 0, and then back down to pi over 2, which is at negative 1, and that's one wave of my cycle. And then I repeated that process again for the second period of the function. Okay, so we have definitely graphed 2 periods. All right, moving along. I have problem D, which is right here. I wrote them backwards on this sheet of paper, so I'm going to cover up E while we talk about this one. So 1D is y equals 2 plus 3 cosine 2x. So a couple of things to keep in mind. That 2 plus up here is a vertical translation. It's sometimes in trig functions comes in the beginning. We're used to in Algebra 2, it was most of the time at the end. So just be cautious of that, which means the graph has moved up 2. So the amplitude now is this number right in front of cosine, which is 3. The absolute value of 3 is 3. That means we go up 3 from the center and down 3 from the center when we graph. The period, b value is 2, so 2 pi, because that's the period of the original cosine function, divided by the b value, which is 2, leaves me with a new period of pi. So that means in terms of my transformation point, I'm going to multiply the angle by 1/2, and I'm going to multiply the cosine value by 3, but then I'm going to add 2 to it. Okay, so as I calculate my values, I get a new table. Now there are a couple of interesting things about this problem, and that is that you are shifting it up, which means the middle line is no longer on the horizontal axis. So you need to shift the middle line up, and I need to see this in your graph. If I were grading this as an assessment problem, I would definitely deduct points for not showing the new middle line. So any trig graph that moves up or down, you got to be sure you're including that as part of your graph. Then I can go through here and plot my points. So at 0, I'm all the way up here at 5. And then, I'm at my middle line, and then I'm below, and then I'm at my middle line, and then I'm above. So you can see that principal graph right there, that first V graph, and then here is the second period, and technically here's the third period. I can reflect it over and move my way backwards, but just be careful because you're up here, so now you have to go to the middle line and then back down and up to the middle line. You can't just carry the pattern out that you've been looking at. You've got to make sure you continue the pattern. All right, then we have 1e. On 1e, we have y equals 1/2 sine x plus pi over 3. So a couple of things. We're back to sine graphs, so we want to be sure that we're using the sine parent functions. Our amplitude right here in front is 1/2, so that is 1/2. The absolute value is 1/2, which means from the center line you go up a 1/2 unit and down a 1/2 unit. The period for sine is 2 pi, but we only have a b value that's 1, so that's really not going to change anything. It's just going to stay the 2 pi that it always has been. So transformation-wise, I'm going to shift this to the right pi over 3. So I'm going to add pi over 3 to all my angles, and then 1/2 times sine means I'm going to multiply all my sine values by 1/2. So remember, when I take pi over 2 times pi over 3, I have to get a common denominator, which is pi over 6. So that is going to be 3 plus 2, which is 5 pi over 6. Remember, you could smile something like that real easy if you needed to. We've talked about that little shortcut where you multiply, multiply, and multiply straight across. So in any case, you're adding pi over 3 to all of these, and these become your new values. And all of your sine functions are going to get multiplied by 1/2. So I take all of these values times 1/2, and that gets me my new points. So then when I go about graphing them, I have at pi over 3, I'm at 0, so you can see where it did shift over pi over 3. And then you have your points up, middle, low, middle. So what that means then is if you're going to continue backwards, then at that point you have to go down, middle, up, middle. So you have to be really careful about that when you're doing that. And typically that's preferable to just making this big long line and not having a very accurate graph if you try to continue off your graphing space. All right, so that takes care of the first part and all of those basic graphing problems in your notes. Now we're going to look at the next set of problems. So we have talked about, and we went through all of these problems right here, A through E. The last few problems are just a little, they're not quite as many, so we'll go through those. So right here, I am on number 2. I am looking at f of x is sine of 3x, and g of x is sine of negative 3x. So we know that when it's 3x, we're going to multiply the x value by 1/3 and keep the sign the same. But over here, we're going to multiply the x value by negative 1/3 and then keep the sign values the same. So we generate our list of points just like we've been talking about. And now we have a graph. So here's my graph of f of x, with this being my principal period. And here is my graph of sine of negative 3x, and here's my principal period. So as I'm looking at these, I want to think about, if I were going to describe these, what would the relationship between the two graphs be? First off, hopefully you can see g of x is a reflection over the y-axis, because we know that. Even if you didn't know the graph, you should know that from looking at the equation. They have the same amplitude because there's a 1 in front of each one. They have the same period because you would take 2 pi, which is the original period for sine, and divide it by the b value, which is 3. So now I get 2 pi over 3. So that's my period, and that's the same for both of them. And they also have the same amplitude, which would be 1. So there are lots of other things that you could say. Those are just some of the descriptions between the two. On question 3, you're sketching them on the same graph, and you're doing it on the same graph this time so that you can see the behaviors up close and personal, if you will. So we are graphing f of x, which is 2 cosine of 2x, and g of x, which is negative cosine 4x. So in terms of transformation points, on f of x, I would multiply all of the angles by 1/2, and then I would multiply all of the cosine values by 2. And then, because right here inside is 2, so the reciprocal is 1/2, so that's what you multiply the x's by. The 2 in front is a vertical stretch, so you multiply the cosine values by 2. Your period would be 2 pi over 2, because the original period of cosine is 2 pi. B is 2, so when you divide that out, now I know my new value, my new period is pi, which means if I'm looking at the graph, then all of this has to happen before I get to pi. The amplitude is 2 because now you're going to go from the middle up 2 and below 2. And so when I get f of x graph, which is this green graph right here, this is my graph that's happening right here, that big W. You can easily see nicely on this one how if I folded this half up and this half up, everything matches up, so it is an even type function. All right, on the other side, we have a reflection over the x-axis and a horizontal compression by 1/4. So that means we're going to multiply the x values by 1/4. Then we're going to multiply the cosine values by -1. The period of cosine is 2 pi, and we divide it by the b value, which is 4. So my new period for this graph is pi over 2. And then the amplitude would be the absolute value of this -1 that's in front, or +1. So from the center line, you're going to go up 1 and down 1. And so that's what the green graph is right here. So you can kind of see, like when I get out to pi, here was just one V graph, but when I look at the reflection, there are 2 of them by the time I get to pi. You can also see the reflection upside down here as well. All right, so a little practice graphing and getting them on the same axis. Problem 4. We are graphing the sketch of y equals sine of pi x over 4. So it looks like it should be confusing, but let's break this up into the chunks that we know, because you know I always tell you the more you can tie it back to things you know, the less you have to memorize, right? You can't see me, but I'm going to nod for you, okay? All right, so what does this pi x over 4 mean? Well, that's the same thing as pi over 4x. Remember, pi over 4 would be a number, right? Because pi is just a symbol for a number, and then you're over 4. So it's just a fraction, an x. So the period then, period of sine originally is 2 pi. The b value is pi over 4, so I'm going to divide by pi over 4, which means I use the reciprocal and multiply. So look at what happens. I get 8 radians. There are no pi's left. In other words, these are actually going to be nice, pretty numbers because they're going to be whole numbers to graph with. We don't have to worry about decimal equivalents. And then our amplitude is 1 because the number in front of sine is 1. Absolute value of 1 is 1. So my transformation is I'm going to multiply the angles by 4 over pi, and then I'm not going to do anything with my sine value points. So back to my parent function table. I multiplied all of the angles by 4 over pi, and I got 0, 2, 4, 6, 8. Nice, pretty numbers. Nothing changed in my sine value column. So when I go to my graph, notice this axis is where we would normally say they're angles. Well, they are angles. They're just in radian measure. So this is radian 2, 4, 6, 8. And then I went at 0. I'm at 0. At 2, I'm up here at 1. At 4, I'm at 0. At 6, I'm at -1. And at 8, I'm at 0. So you can kind of see that sine wave right there. And so if I want to do a second graph because I don't want to run off my page, then I just continue the pattern, right? So I go down to the bottom and then back to the middle line, up, and then back to the middle line. Okay? So that's just kind of showing you that you can have some nice numbers. They aren't always going to be yucky decimals, and sometimes they may not even have the pi in them because they'll be pretty radians. All right, last one, guys. So on this last one, we're going to graph on the calculator and sketch your graph. Select a good viewing window. So a couple of things to remember about graphing with trig is that there is a thing called zoom trig, and we love it because that helps us set it to what we need. What we have to be careful about is what unit we're in, because you could do zoom trig and be in degrees, or you could do zoom trig and be in radians. So when I look at this problem, I see, oh, there's pi, so I know it's in radians. So the first thing that I would do would take my handy dandy calculator, and I'm in a mode for demonstration here. Let me get back into normal stuff real quick. Okay, so I'm going to go to my mode, and I'm going to make sure I'm in radians, which I am, so I'm good there. And then I am going to make sure I know my period and my amplitude. So sine has an original period of 2 pi. So that's 2 pi. I have a b value of 4, so I'm going to divide by 4, and so I know my period is pi over 2. The amplitude, the number in front of sine, is -2, so the absolute value of -2 is 2, and so that gives me my amplitude of 2. That means from the middle line, it's going to go up 2, and it's going to go down 2. Now, as everything else we've ever done in graphing, we always isolate the b value. So that means I'm going to divide this by 4 and this by 4. And that leaves me with the 4 that's pulled out, an x plus pi over 4 inside, which means we have a reflection over the x-axis, a vertical shift by 2, a horizontal compression by 1/4, and a horizontal translation to the left pi over 4. Okay, so there's a lot of stuff going on with that graph. So the first thing I'm going to do now is go into my y equals, and I'm going to type in my graph, which is -2 sine, and then inside I have 4x plus, and then I'm going to have my pi symbol, and close it, and double check myself. -2 sine, oops, I got a couple of sets of parentheses there. That would possibly mess things up, so let's get rid of one of those. And I have -2 sine 4 pi plus pi. Great. All right, so we knew basically from looking at transformations what should be happening with our graph. And I want to use a good window, so I'm going to do zoom trig, and that's just where we normally do zoom 6. We're just scroll down here until we hit zoom trig instead, which is number 7. And it will step out that graph for me and set up a decent window. Look at that thing go, right? All right, so that's a lot of stuff. Do I know what that means? Do I know what those numbers are? And so look at your window to help you decide. Okay, if I want to think about this in terms of just knowing, because right, you want to control the graph. So I know that my x-axis is this way, and let's go from negative pi over 2 to pi over 2. So my x-min, that's the farthest to the left, is going to be negative 2 pi. And then the positive one's going to be 2 pi. And then we're going to count by pi over 2's. So that's my scale. And then we can leave the y min and y max at 4 and 4. That's going to be more than we need, and a scale of 1. So when I graph it, you can see I'm still getting all those waves, but that's just me controlling my graph just a little bit so I know where it's starting and stopping. All right, so if your window for this problem was you wanted it to be a period of pi over 2, that means you want it to end at pi over 2, right? So you want that to see that graph happening. So let's change our window just a little bit so you can see that before we finish up here. So I'm going to go from negative pi over 2 to pi over 2. And then I'm going to have an x scale of pi over 4 because that's kind of halfway between. Now I'm going to go, I didn't really do too much stretching or compressing. I know it's going to 2 because that's what the vertical stretch or compression is. So I think I'm going to make this just a tad bit smaller and go from 3 to 3. And then when I graph this, you can see a very different graph from what we saw a minute ago. And you can see 1 period and you can see 2 periods. So we have the period from the positive rotation around the unit circle, and we have the period for the negative rotation around the unit circle. So that one's going in the opposite direction. So you can definitely play with the window on the calculator. Just be careful because if you're in radian mode, then you need to count by pi over this or pi over that or go to 2 pi. If you're in degree mode, then maybe you go from negative 360 to 360 and you count by 90 degrees. So you definitely have to be careful because if you try to count by degrees and your graph is in radians, you're going to get some really, really crazy looking graphs. All right, my friends, that wraps up the sine and cosine graph. Again, you're going to use these graphs when we do secant and cosecant, so it's really important that you get a good grasp on this. And the written notes of these are on Canvas as well, and there is a little demonstration link on there to show you the unit circle unwrapping and making your sine curve. So you have some resources there. Don't forget that in the help section you have the list of transformations for trig functions. So if you need that reference, it's there. And then I will see you next time when we learn and practice more sine and cosine graphs, because we're going to use those to help us get the secant and cosecant graph. Thanks so much, guys. Bye.